Hello everyone, this video is about Pure Mathematics 3 differential equation past paper questions. Number 1, we have this example. Maybe just read the question first. We have the equation and we have the boundary condition when x equals 1, y equals 1. So the first step is to separate the variables. So from this equation we can move the y to the left, we divide, and move the x to the right, and also move the dx to the right. So we have 1 over y dy equals 2 minus x squared all over x dx. Integrate both sides. You can split the fractions. The integral is ln y modulus of y equals, here we have 2 times ln x minus 1/2 x squared plus a constant, let's call it c1. We can raise both sides with the same base e, get rid of the ln on the left. We have only the modulus of x, the modulus of y, and on the right we have e to the power of something, which is always positive, so don't need to use the modulus, just y equals. And we can now move these two inside the logarithm as the power of the argument. So we have just x squared, because e to the power of ln cancel out, and this is e to the power of this, and times e to the power of this, times e to the power of c1. You can split the exponents, and this is something squared, which is always positive, and this means we have c, just the constant, times x squared times e to the power of minus 1/2 x squared. Plug in 1 1 when the x is 1, y is 1. We can find the value of c. This is the value of c in the simplest form. Therefore the equation is y equals this in terms of x. Just replace this c with the value of c, and you can recheck by, well, first of all, 1 1 must be on this function or on this curve. So when you replace the y with 1, the x with 1, the equation must be true. And if you just use your calculator on the right, you will get 1 here. Now if you want to check the differentiation, we have to use the product rule. Let's say this is u, this is v, u prime v plus v prime u. We get this, and we can this is 2 over x times, so here we pull out this y here, which is e root e x squared e to the power of minus 1/2 x squared. So that is why we have, this is x originally. If we want to pull out over x, we have x squared, or we gotta make the thing inside the brackets here exactly the same as the y or expression, or this expression on the right. So that's why we have 2 over x here, so that when you multiply, you have back the original term here. And here we can pull out everything. We get, this is y actually here, so that's why we have 2 over x times y minus x times y. And then yeah, we multiply by x both sides, because that's what we have in the original equation, and we get simply 2y x squared y. You can pull out the y, we get this, which is exactly the same as our original equation. So this means it checks, we do have the right solution. Second example, almost exactly the same. So you just maybe read on your own here, and this is how we check. So exactly the same kind of question. Next example, trigonometric, a bit different. So here we divide both sides by x plus 2. So we move the x plus 2 to the left. We move the sine 1/2 theta to the right. So it's divided by sine 1/2 theta. And we multiply by d theta, so the d theta is on the right. And now in case you're wondering, why do we have to multiply by 2 and then divide by 2? Well, because we need the numerator here to be the derivative of the denominator, so we use the ln rule. The derivative of sine is cos, but we have 1/2 theta. Chain rule, we have 1/2 cos 1/2 theta. That is the derivative of sine 1/2 theta. and therefore we have ln, and raise both sides to the same base e. And now you don't need to use modulus here, because actually the MF19 formula allows us to just use brackets or parentheses because of the restriction. Look at the formula derivation video if you're interested. So no need to use modulus. And now you can plug in when the x is 1, the theta is 1/3 pi. So we replace, before we replace, we simplify things here. So we use the cos double angle formula, and we get sine squared equals this. So in the question it says in terms of cos theta, so that is why we use the double angle formula, because we want it in terms of cos theta. So we use this identity. Sine squared can be replaced by 1 minus cos over 2. So this is the over 2, 1 over 2. So we have c2 times 1/2, which is another constant. Let's call it c. We still have minus 2. And now we plug in the 1 and pi over 3. We get the value of c, and therefore the final answer is 4 minus 6 cos theta. Now usually we reject analytically like this. If you wanna differentiate, it's gonna be like this if you differentiate, but there's another way to check here using your calculator. So when theta equals 1 radian, why do we use 1 radian? Because it says the theta is between 0 and pi. Pi is around 1.57, so we can use any random number such as 1 to check this our solution here. So let's use 1. This is totally random. When the theta is 1, the x is, well, because the x is here from our solution. Based on our solution, if our solution is right, when the theta is 1, the x is, use your calculator, 4 minus 6 cos 1 radian. We have to use radian. We get 0.758 and so on. And the ddx, the dx d theta when theta equals 1 equals this. This is again by using the calculator, the derivative function in the calculator. But in the calculator, we can only use ddx. So this is ddx of the function. So actually this is dx d theta. This is x. So d, this guy, d theta, which is the same as d, exactly the same, but we replace it with x, same thing. Right, so we are differentiating this with respect to theta, and then we replace the theta with 1 radian. So we get this, and now we check using the original equation, sine 1/2 theta dx d theta. Sine 1/2 times the theta is 1 radian, times dx d theta, which is this value, is equal to x plus 2 cos 1/2 theta. The x is this value here, this is x, so x plus 2 cos 1/2 theta, the theta is 1. And as you can see, the left hand side is exactly the same as the right hand side, so we stand corrected, we have the right answer. So this is how we can check using the calculator. Alright, now maybe you can just read the rest on Google site. Alright, that's it. I'll see you again next time.